Hello, you are listening to the Bombast broadcast, and I'm your host, Eric Lindell. Today, we have an incredibly exciting topic having to do with the underlying ontological nature of information. Information comes in two forms, just like consciousness does. If we may confine our discussion to discrete information, those two forms would be very simply data and algorithm. Where algorithm is the agent of change of data. Now, up to this point in time, it's widely recognized that data is a form of information, but not that algorithm is. More to the point, they are interchangeable, as are, for example, mass and energy. And we'll have much more to say on that structural isomorphism hopefully soon. If you want to represent data as an algorithm, all you have to do is write an algorithm that will print out the data, hence the equivalency. If you want to write an algorithm as data, then all you have to do is specify the Turing machine, if we're talking about an abstract algorithm, as zeros and ones or whatever symbols you happen to be using. Or if you're talking about a program for a digital computer, then all you have to do is write the program. So you have this interchangeability of data and algorithm as two fundamental ontological forms of information, fundamentally different in that algorithm is active, data is passive, fundamentally similar in that each is understood in terms of the other, and each is transformable into the other. Okay, now, what does that concept of intertransformability sound like? To me, it sounds a little like special relativity and the transformability of mass and energy. Now, when you have a particle with a certain mass, where are you likely to find it? Well, it might be anywhere in all of space, but it is assuredly located in space. Mass and matter are always spatial. And where's data? On a Turing machine's tape. It's in computational space. It's not the same thing as physical space, because the tape that contains the zeros and ones as input and output is conceptual, as are the zeros and ones themselves. But it is assuredly spatial. So what about algorithm? Well, now it should be kind of obvious. Algorithm is temporal. That's why you have algorithms classified according to their asymptotic temporal behavior. Some are polynomial, some are exponential. That's neither here nor there. The point is that the active, which in this case is algorithm, is always temporal, and the passive, in this case data, is always spatial. Moreover, we might go so far as to say that as long as we're making an analogy between data and algorithm as forms of information on the one hand, and on the other mass and energy as forms of physics on the other, and we've already pointed out that matter is spatial, that algorithm is temporal. So what is it in physics that's also temporal, like algorithm? Well, energy expenditures. Okay, energy is always expended in time. That's why you have, such a thing as a joule, which is a certain amount of energy, and a watt is that amount of energy expended in 1 second. That's why you have units of power that are the rate of energy expenditure in time. So you have both algorithm and energy being temporal. What else do you know about the connection between algorithm and energy? Well, probably not enough, given the way this subject is taught, or the way it was taught to me anyway. But What's the first thing you do if you want to run a PC even before you turn the thing on? Well, I think everyone knows, unless it's a battery-powered laptop, you plug it in. And even if it is a battery-powered laptop, the first thing you do, or I should say a prerequisite for turning it on, is the bloody thing has to have some power, because executing an algorithm necessarily involves an expenditure of energy. So when we talk about this passive-active duality in information as data and algorithm, and we make a parallel with the passive and active nature of physics, namely mass and energy, we're not kidding around, okay? We have numerous ways of demonstrating that this is not mere semantic coincidence, but rather an underlying structural isomorphism of tremendous significance, which is going to come in very handy for a unifying theory of information physics and maybe a couple other things. I don't want to get too redundant with my other videos, because then you might stop watching them. So let me stop here before I ramble. And I do thank you all who are watching. And if you're not watching, why not write in and tell me why? Until then, best wishes from all of us at the Bombast Podcast. I'm your host, Eric Lindell. Have a pleasant day.